over and over and over again. So the way I like to set these things up is a little bit different than what textbooks do. It's a little bit different than what the other classes do and all that as well. I try to set these up to turn them into like one-step algebra problems and so on and so on. But it all depends upon visualizing it, understanding what goes where. So the first thing I like to look at is I'm going to look at the an equilateral triangle. Let me put this on a clean page here real quick. Equilateral triangle. What do you guys know about an equilateral triangle? All three sides are the same, and what about all three of the angles? They're how much? Well, they're all 60. Yeah, they all added 180, so all three of them, like each one of them is 60. So I know that I have three 60-degree angles, and I also know that all three of my sides are the same. Okay, that's where equilateral came from. From that, I'm going to draw what's called the perpendicular bisector. You guys vaguely remember that? It means it's bisected and it's perpendicular. So if I do that, erase this with a little space here. It's going to go from the peak down to here. And if it bisects this side, I know that those two parts are going to be the same. Okay. Now, let's give this triangle some numbers real quick just to make it easy. Let's say sides are 8. If this is 8, that's 8. What do these two sides both have to be then? 4 is good. Okay. Now, if you look at the triangle, I have that perpendicular bisector. That perpendicular, bless you. That perpendicular bisector creates a right angle down at the bottom here, correct? That's what that symbol means, right? So go back again. How many degrees are in a triangle? 180. So if I take out the 90, I'm looking at just one triangle right now. I take out 90, how many degrees are left? 90, right? So if I take out 60, how many degrees are left for up here? 30. And isn't that the same on the other side? Yeah. So by drawing in what we call the perpendicular bisector of an equilateral triangle, we get what's called a 30, 60, 90 triangle. Okay? Now, if we look at this one, are you guys okay in saying that, let me block off half of it real quick. Are you guys okay in saying that this side here is a right triangle? Yeah. Do we know the hypotenuse? Yes. Do we know, then we obviously know one of the legs, correct? We don't know the other leg, right? So if I wanted to solve for the other leg, I just have to use Pythagorean theorem, correct? So if I say x squared plus 4 squared equals 8 squared. Everybody okay with me so far? Kind of mirrors out what we did last week, right? I didn't expect you. It's okay. Not smile, right? So in this case here, is everybody okay that that 4 squared's got to get moved over to the other side? Yeah. All right. So I'm just going to write it out first. Now I get x squared is going to equal 8 squared subtract 4 squared, which means I'm going to go to my calculator. Just round one. Use my other calculator. So in this calculator, we clear out what we have. X squared minus 4 squared. I get 48. How do I undo square root again? Square root, good. Now, in these calculators, if I hit second square root, and then I go back, second, remember the answer button? We're going to use this answer button a lot. And then I hit enter. I get 4 root 3. Everybody see that? Okay. Now, square root of 3, that's just some number, isn't it? Remember, these calculators keep things in what are called simplified radical form. All right. Now, let's say, excuse me, let's say we change this just a little bit. Instead of having 8s, let's say that these guys are, now let's go 12. And then this would have to be 12, and then these would have to be how much? 6s, okay? Again, if I look at it, I'm still looking for a leg here, aren't I? All right, so we're basically set up the same problem with just different numbers. All right, watch what happens. So I'm going to call this, again, we'll just call this a squared, guys. Then we have 6 squared is 12 squared. So our a squared will be 12 squared, subtract 6 squared. Then go back here, 12 squared, subtract 6 squared. And then square root of your answer. And I get 6 root 3. Another root 3, isn't it? Okay. What's that?
The same as using triangles.
What do you mean?
Just as a figure of speech, not for real and being.
Oh, I got you. No, what's happening here is that no matter what, when you have an equilateral triangle, whenever you have an equilateral triangle, you put this on here together. Whenever you have an equilateral triangle, these guys are all, if this is 1, what's this? 1, which means the whole side is how much? 2. Okay. Correct, the other side is also 2, very good. Now, if I go back to here and I want to solve for that again, isn't that again 1 squared, or x squared plus 1 squared is 2 squared? You guys okay with that? So this is no matter what, this value every time is going to have that multiple of a square root of 3 next to it. Because as things get larger, we scale them bigger to different sizes. Do the angles ever change? Nope. You always get that angle-angle similarity. You always have the same angle values. What happens is the sides have this proportionality to them. They have the same common rates. What's that? Correct. Now what happens is you get this special pattern that angles are looking at sides opposite. This was the 60, correct? So the 60 looks at the side opposite here. This was the 30. This looks at the side opposite here. This is our 90, and it looks at the side opposite here. So, what's that?
How do you get 30?
What's half of 60?
30.
Remember what I did was, when we drew this down, this was 90, this was 60. This creates a triangle. There's only 30 degrees left that go there anyway. Then it flips the other side as well, all right, because of the equilateral. So what happens here is you get this, what's called a special pattern of a 30, 60, 90, 100. No matter what, we're going to use this kind of over and over and over again. Doesn't that work? I'm using these values of x as some common multiplier. Okay? No matter what, this ratio of the sides always occurs within what we call this special right triangle. Across from the 30 is always looking at some value of x. That's why I like to use arrows. It's looking at what's across from it, what is opposite me. Okay? Opposite the side of 30 is some value of x. Circle, I look. Opposite the 60 is some value times the square root of 3. And then opposite the 90 is always double what's across from the 30. And it goes back to the idea that if our side length was 8, when I got bisected, it was 4. If I doubled 4, it would be 8. That's where this comes into play. Okay. Now, by knowing this, if I know that I have this type of triangle, and I know just one side length, I can find all the rest of it. That's where the special triangles come into play. Okay. For example, there's only going to be 2 special triangles. Right? And that one has its own pattern as well, but it kind of follows the same premise. Okay, and we'll talk about that one here in a minute or two. But like I was saying, this basic idea here is the whole background of what we call the unit circle in Algebra 2. Do you guys agree that if I go around a circle, is how many degrees? 360. So this is 0, this is 360. This would be halfway at 180. Are we okay with that? What's half of that? 90. Okay. So what happens is you have 30 degrees here, you'll have 60 degrees here, and it just continues itself through with different multipliers. Okay? Obviously, this is nothing you have to worry about now, but this is stuff that you'll use later on. These values here are the same as they are here, as the things move around. Okay? The way trigonometry works, when we get to this stuff, this is how all your angle values work themselves through. Okay? Now, here's what will happen. In a triangle like this, you'll have a picture, you'll have an angle. It might give you the 60, it might give you the 30. If it gives you a 30 or a 60, it means it's a 30, 60, 90 triangle. And let's say we know across from one of the angles, for example, let's say across from here is 20. And I need to figure out the other two sides. Here's the way that we do this each and every single time. I like to call this, you guys ever heard of the term using like a jig, like a metal jig or a wood jig? You know what I'm talking about? You ever heard of that before? A jig is something that you use when you're building stuff to kind of replicate measurements. For example, sometimes if have you guys ever help out building a deck or putting up railings? You gotta cut a bunch of the wood to make certain heights and all that. Instead of measuring each piece over and over again, what people normally do is they make a slot, they slide it in there and they cut it. Slide it in and cut it. So if you're replicating the same thing over and over again, you're using a tool to help you make that efficient. You probably do that in the kitchen. You know, you probably have stuff like that. It's just something that helps make your life easier in terms of this. This is just what I call an algebra jig. So I know that in this picture here, it's a 30, 60, 90 because there's a 60, okay? I write out 30, 60, 90. I know across from this is some value of x. Across from this is x times the square root of 3. Across from this is 2 times x. I look at my picture. Like I said, it's just tremendously visual. Across from what angle do you know? The 90. I know that the 90 degree angle is looking at a 20. So that means this value here has to equal 20. What do I do to solve for x? This is the pattern that always occurs. This pattern will always be here. Okay? Isn't that a one-step equation? What do? Divide by 2, right? So what's your value of x? So that means everywhere I see an x, what do I replace it with? 10. So this would be a 10. This would be a 10 root 3. That's what this means. Using this little algebra jig, if you will, 30, 60, 90, this pattern always occurs. It never changes. Okay? You need to write this out every time. You set it up and go. Alright? It is super simple if you break it down into this setup. Okay? Again, it just depends on which angle, across what side you know. Alright? Each one of these is a simple equation. Alright? Let's try another one. Oops. Let's say this is a weird. Okay. So in this problem here, got a right triangle, and I have a 30 degree angle with it. So is that a 30, 60, 90 triangle? Has to be, because you've got a 90 and a 30, so it has to be that. So the first thing you always do, 30, 60, 90. Across from them is some value of x. Across from this is x times the square root of 3. Across from this is 2 times x. you're going to set it up the same way over and over and over again. All right? So, looking at that picture, across from what angle do you know? The 60. I know that across from the 60, even though it's not labeled, I know this has to be a 60. It equals 8 root 3. Remember, this is just x times the square root of 3. How do you undo multiply? Divide. So to figure out what the value of x is, divide both sides by the square root of 3. What's the square root of 3 divided by the square root of 3? 1, right? What's anything divided by itself? 1. So what's x? 8. So that means anywhere I see an x, what am I going to put? 8. So across from the 30 is 8. Across from the 90 would be 2 times 8, otherwise known as 16. Okay. Same thing over and over and over again. Now, what's that? Not gonna lie, there will be a weird time from every once in a while with the roots, okay? But that's why we have fraction bars and the multi-view calculator, because it doesn't work. Yes, ma'am?
So if the 16 is already right there, will we divide it instead of multiplying?
If the 16 was there, across from the 90?
Yeah.
Well, again, yeah, because then I would set this part up that it equals the 16 to get value of x divided by 2. Every time you're trying to figure out which part you know, then you use that little one-step algebra problem to go for it. Okay? So, same idea. Let me show you the weird case. Again, it's a 30, 60, 90. It doesn't have to have all the values in there to show that it is. It just has to have one of the angles. So you can put the 30 in there. All right. So, same thing. I always write out my start. My start says, hey, 30, 60, 90. I write them through. Across from the 30, some value of x. X times the square root of 3 is across from the 60, and 2 times that value of x is across from the 90. According to the diagram, across from what angle do you know? The 60. So I have the equation here now of x times the square root of 3 is 12. Once again, how do you undo multiply? Divide. Okay, so we move this down a little bit. In your calculator, you literally type in what you see there. Fraction bar, 12 over the square root of 3, and hit enter. And it gives you an answer. Sometimes the answer might just be 4 root 3. Sometimes it could be 2 root 3 over 3. It all depends on what the numbers are. Yes, that means the value of x is 4 root 3. Which means everywhere I see an x, what am I going to put? 4 root 3. So across from the 30 then is 4 root 3. Across from the 90 would be 2 times 4 root 3. Well, what's 2 times 4 root 3? It's 2 times 4. 8. So it's 8 root 3. If you weren't sure of that, could you press the button in the calculator? Hit times 2. And lo and behold, it does the math for you. Okay? It does it for you. Again, it's nothing crazy. You know, across from the 30, that's the 4 root 3. And then this was 8 root 3. Okay? It's completely fine. These are just, excuse me, these are just roots. All right? They just represent decimal value. Right? That's one of the triangles. The other triangle is what we call a 45, 45, 90. Okay? And that one came from a square. What do you guys know about a square? All 4 of the sides are the same. And then you've got 4 right angles. Okay? Now, if I draw in a diagonal, and I only look at half the square, I draw on the diagonal here. What kind of triangle, don't say right, what kind of triangle does this become? Bless you. It's a right triangle, correct. But, a what? It's not 30, 60, 90. It's, well, isn't it isosceles? That's what I was trying to get at. Everybody see that it's isosceles because you've got the two sides that are the same? If you have the two sides that are the same, that means you have to have the two angles that are the same. And that's where the 45s come into play. There only being 180 degrees in a triangle, you subtract out 90, you're left with 90. Since these two have to be the same, that's where they get 45s. That's where that comes from. All right. So this one you'll see drawn either with the side markers being isosceles, or you'll see it drawn with the two tick marks for the angles, or it might just put a 45 in one of the corners. Either one of those representations tell you it's 45, 45, 90. Okay? So let's do the same idea we did a second ago with the other triangle. Now, if I have this one, isosceles right triangle, and let's say both these side lengths are 5. If I know my side lengths, what do I do to figure out the hypotenuse in this case? Is the hypotenuse the A, B, or C from there in the C? Okay. So what happens then is we're trying to figure out this. Let's just move it. We would wind up with 5 squared plus 5 squared is C squared. We are with me on that one? All right. Go to the calculator. You get 50, good. Now what do you do to undo the squaring again? Square root it. So again, use the calculator, square root of the answer, and I get 5 root 2. Okay. The pattern for this also never changes. No matter what, your two sides have to always be the same because they're isosceles. So what happens is you wind up with the pattern for these, for a 45, 45, 90 triangle. You get that pattern. The two side lengths will always be the same, and there's going to always be a square root of 2 now on the hypotenuse. So the way that I write out the algebra jigs, like I did the other one, 45, 45, and a 90. All right. Remember, you might not see the angles drawn in here. It might just mark them with the tick marks. It could mark them like this, or it could just put a 45 here. All right? It could be any one of those methods. It's going to be all the same. So you know the opposite that we're looking across from the 45 is this value of x, which means across from the other 5 also has to be some value of x. Then across from the 90 is x times the square root of 2. Now, I'm using this value of x for all of this. It just means it's some constant. Okay? It's just this constant multiplier. And it's just the easiest way to write them out. This one's a little bit easier to deal with because you only have to solve for one. For example, if I have a picture, let's reuse this one. And I know this is 7. Is that opposite of 45 or opposite of 90? 45. So I know that across from one of the 45-degree angles is 7, so that means the x value has to equal 7. Which means everywhere else I see an x, what do I put? 7. There you go. Okay. It doesn't change. It doesn't change. The only thing that's a little bit weird with this one is if you're given across from the 90 and it doesn't have the root 2. For example, is it a 30, 60, 90 or 45, 45, 90? 45, okay. Remember, it has to be 45 because the isosceles. If the two legs are congruent, that means the angles have to be congruent. That doesn't change. Right? So as you go in here, again, you write it out. Looks at some value of x, looks at some value of x, looks at some value of x times the square root of 2. So, across from which one do you know? The 90. So that means that this x times the square root of 2 has to equal 30. What do you do to solve for x? Yep, divided by the square root of 2. Now, again, you have to use the fraction bar with these things to make this work correctly. Yeah, because if you don't, it'll give you the decimal. So, fraction bar 30 over the square root of 2. And then it'll give me my answer of 15 root 2. All right. That means my value of x is 15 root 2. So everywhere else I see an x, what do I put? There you go. That's all this means. It's a matter of deciphering which of the two triangles you're working with, and then just substitute in which value you're working. You're just go for it. All right. So with special right triangles, all you need is one side length, and you can figure out everything else. All right. For example, wait. I'm sorry. No problem. Didn't mean to get out ahead of you there. All right, here we go. Here's an example. Now, I'm going to kind of cross off more often than not, quizzes and tests and things. I'm going to ask you guys to solve for all the missing side lengths, not just solve for one value. A lot of worksheets and stuff, just put in variables for things. I try to remember to white out all the variables, but sometimes I don't. So, in this case here, I just crossed off what they call x. So, first thing you have to figure out, which of the two triangles is it? Why? Because it says it. All right. So it says that it's a 45. So start out, fill in the blanks. 45, 45, 90. Across from which angle do you know? You know one of the 45s, which means x is 4. So everywhere else I see an x, I put. So in my diagram, it would be a 4 and a 4 root 2. Not that bad, is it? The idea is you got to know how to use these. You know how to use these, you're going to be fine. Right? You know, you're going to this value here. And that's good, because with these, if you know across from a 45 and one of the isosceles ones, you should be able to do it without having to write it out. But if you forget, is it all right? Absolutely. Again, try to oversimplify it. Notice, all I'm doing, once I know what the value of x is, I'm just substituting in. I'm not mathing it any further. There's nothing else for me to do. Okay? All right? What's up? All right, again, go back to this one here. Is it a 30, 60, 90 or 45, 45, 90? 30, 60, okay. So again, we write it out. Fill in our blanks. Some value of x, some value of x times the square root of 3, and some value of x times 2. Across from which angle do you know? 60. So if I know across from the 60, I set this equal to the square root of 3. How do you get x by itself? Divide it. Okay. Again, divide both sides by the square root of 3. Square root of 3 divided by the square root of 3 is how much? 1. So what's your value of x? 1. So that means everywhere I see an x, I'm going to replace it with a 1. If it was the square root of 3, if it's the value that's in front of it is a 1. So we're solving for whatever that multiplier is. Because if it was the square root of 3 times the square root of 3, it would have been a 3 across from the 60. Alright? Because then that meant that the x value was the square root of 3. Remember, even though there's nothing there, you're still solving for it because the coefficient that you don't see is 1. That's the little trick of it. That's the little trick. Remember, Sam, a little bit ago, I think I did, was it this one? Remember how we wrote it out, or which one was it? I remember how I did the sides of 1, 2s, and 3s? So if I put a 1 here and a 2 there, 2 squared subtract 1 squared was 3, and this gave me the square root of 3 on the other side. That meant the multiplier was 1. That's where it comes into play. Let's see where we are here. Remember, a lot of times the images and stuff that we might end up using, they'll have variables for the missing side links. Sometimes those variables say x. Remember, that's a different value than what you're looking at here. Just think of it as your missing side link. Right? Think of it as a missing side link. Okay. So first thing, you have to make a decision. Which of the two triangles is it?
369.
Correct.
So,
okay, so what you gotta find is the value. So you equal, since you see 90, across 90, you equal 2x equals 6.
So 2x.
Divide that, which will give you a 4.5, and then your value for x is going to be the rest.
What's the value of x?
4.5. I got one. Oh, you put 6.
You might have written down the wrong number.
Yeah, there you go. That's 3, and then you plug it in, and then we'll bang up on it, we'll get out of here.
Now, I'm glad you made that mistake, Christian, because this stuff is so easy to look up and type down the wrong thing real fast. It happens all the time, all right? So if that was the case, if that just meant you bumped the 9 because it's directly above the 6, and that's all right, okay? Because you probably, that's why I need you guys to write out what you're doing. So if you do something like that, I know you just hit the wrong button. And then if you hit the wrong button there, but yet you did the rest of this correctly, were you wrong? No.
You got the whole form right?
Yep. And this happens so often in math. That's why it's so unbelievably important that you guys got to write this stuff out. All right? That's the big thing in this one. All right? One more and I'll give you some problems to try.
Huh?
Huh?
I'm just on 45, 25.
Bless you.
How you on 45? What'd you do again? Right there with the name. I can't take that.
Which one is this?
This is 45, 45, 90.
Good. This is 45, 45, 90. So we know across from a 45, so we got 45, 45, 90. Correct? Correct. So if that one's 10, this one has to be 10, which means across from the 90 is how much? Not 10 over 2.
10.
Roots, yeah. Roots. Very good. Now, in this one here, I hope so. Now, in this one here, guys, one thing I want you to notice is that don't worry about where it says all the variables, A's and B's, X's and Y's, U's and V's, and all that. What I want you guys to do is solve for each missing side length. So we're basically doing the same thing I was doing here. When I got to the problem, you notice how I just kind of scribbled out the variable real quick? Do that. It just I just didn't get a chance to wipe these things out because I'm trying to run these off as quickly as possible. But I do want to flip over and look at number 12 real quick. You flip over and look at number 12. Well, which of the two triangles is it? 30, 60, 90. It's got to be because there's a 60 in it, okay? So that means we write out our 30, 60, 90. All right? And I left plenty of space the way this was written out so you can do all your setups for each one of these without too much of a hassle. Across from which angle do you know? Remember, the 60 opens up to here. This has to be the 30, okay? So that means I'm looking at the value of x is 5 root 3 over 3. So everywhere I see an x, what do I replace it with? 5 root 3 over 3. So I can get then 5 root 3 over 3 times square root of 3, and 2 times 5 root 3 over 3. Now the reason why I wanted to show you this one is so that way you guys understand how do you enter that in the calculator. You enter it in literally like you write it down. So if I go to my calculator, fraction bar, 5 root 3, arrow down, over 3, arrow to the right, times square root of 3. Okay, 5. That means across from the 60 is 5. Okay. I do the same thing for across from the 90. 5 root 3 over 3 times 2. Get it? The answer is 10 root 3. Yes. And That's the way the patterns of the things are working. Remember how this worked. Across from the 30 is always half of whatever's across from the 90. Well, if this is 10 root 3 over 3, well, half of that has to be 5 root 3 over 3. I have to multiply that by the square root of 3 to get this. Well, square root of 3 times the square root of 3 is 3. 3 divided by 3 is 1. That's where you get the 5 from. Okay. This should not be terrible. It'll probably take you 15 minutes or so. Because this is my value of x here times the square root of 3. Alright, so you type that in, move the arrow over, times the square root of 3. What's that? Yes, sir. Yep. And that goes with the idea of doing this through. Now, here's the thing, guys. If you don't have this multi-view calculator with you, you can still figure out where everything's got to go. You can still get through most of it, especially if you have the values of x or the 2x. You should be able to divide by 2. If you've got to divide by the root 3's, then I wouldn't worry about doing that, all right? But this is super, super important to have this multi-view calculator if you want to do your work. It's a good way to see it, to check your work. What's that, bud? Yeah, I wouldn't. That way you're not trying to differentiate between this value of x and solving for a side. On quizzes and stuff, Sam, I'm just making sure I can say solve for this and side links, and it'll already be pre-whited out. I was just running short on time when I was making these copies, so that way I just let it go. What's that, bud?